Okay, students, welcome to the class. We will study further about the coordination compound, complex compound. That is Werner's theory. This was the first theory about complex compound and Werner's theory of complex compound. Werner isolated many complex compounds, not one or two, many complex compounds, and he studied their properties. When he studied its properties, then he gave a theory, formulated it, and that theory is named as Werner's theory of complex compounds. So Werner theories of complex compound has three postulates. So postulates of Werner's theory. The first postulate of the theory is this is consists or it exhibits a complex compound exhibits in a central metal atom, or I should say rather that a complex compound has a central metal atom or ion, as we have studied earlier, and this central metal atom or ion exhibits two types of valencies. Two types of valencies. What are these two types of valency? That is primary valency and the secondary valency. Primary valency is based on the oxidation state. Here I write primary valency. This is based on oxidation state of the central metal atom or ion, whereas secondary valency is based on co-ordination number of the central metal atom or ion. Oxidation state, you know, last time we have done calculation of the oxidation state or oxidation number of the central metal atom, with that is its tendency to lose electrons, and the coordination number indicates that how many ligands can be attached to the central metal atom. So this is very important. It is based upon the oxidation number and this is based upon the coordination number. Now the next point which you have to do about the primary valency, that only negative ions, that is anions, negative ions, that is anions, can be attached to the central metal atom or ion. And here negative ion or maybe neutral molecules or maybe both anion and neutral molecules can satisfy the secondary valency. So the third subpoint of the first postulate, primary valency is shown, this is shown through dotted line. When we'll draw the structure, we'll show it through dotted line, and secondary valency will show with non-dotted thick lines. Now, why dotted line and why thick line? Dotted line indicates that the anions which are attached to it are not permanently attached to it when the salt and complex salt is dissolved in water. So when this salt is put in water, so anions which are attached to the primary valency, they get dissociable. So they get dissociated, and so these ions are dissociated when they are dissolved in water. And here negative ions are not getting dissociated when dissolved in water or in the solution. Now the second point, now the second postulate. What is the second postulate for this? The central metal atom which you have or ion, it will always, the central metal atom, this will always, or you can say it has a tendency to satisfy its both valencies. What are both valencies? Primary and secondary. And this is second postulate. Okay. So when this is here satisfying through this both, so in doing that, what happened? Sometimes, how this is done? Negative ions are satisfied with primary valency, and these negative ions are satisfied with secondary also. So some anions will be, negative ions will be attached to the primary valency, and the same anions will also be attached to the secondary valency. And if this is happening, so that anion which is being attached to the central metal atom by both of this, if it is attached to this, so that anion is not able to dissociate in water or in solution. Only that anion which is linked to the primary valency is able to dissociate. So this is the second point. We'll see that in the structure. And the third postulate is primary valency is a non-directional, whereas this is directional. Why this is directional, the secondary valency? The secondary valency is based upon the coordination number. And what is coordination number? That is how many ligands are attached to the central metal atom. So it is based upon the bond between ligand and the central metal atom, and this bond is always a coordinate bond. It is an arrow bond, and coordinate bond no is a directional bond, and so the secondary valency is directional. Here no coordinate bond, simple. Your electrostatic forces of attraction are there, and so this is non-directional. So we'll see now the structure. Just a minute. Check. Now we'll see the structure example. Cobalt chloride with 6 molecules of ammonia. This is the way how Werner wrote the formula. There is no square bracket in all what you have seen previously. So this is 1 mole of the substance. When this is put up in water, what they found that cobalt remain attached to the 6 molecules of ammonia. This part was not dissociated, and 3 chloride ions were separated. So here there were 3 positive charge. This was found. So here it is. 3 moles of chloride ions were given by 1 mole of this compound, and so that indicated what? That in this cobalt, this is having oxidation number 3 here. So this is its primary valency. Okay, means these particles are attached through the water primary valency. There are 6 ammonia molecules linked to it. So coordination number is 6, and that is indicating its secondary valency. So if we draw the structure, then you will find how to draw cobalt. This is having 3 primary valency. Primary valency is shown with the dotted line. They will be at equal distances. So we will show through the dotted line at equal distances. So 3 chlorine atoms, or chloride ion rather I should say, and ions are attached to the central metal atom cobalt through the dotted line. So this is indicating primary valency. And coordination number is 6. So we have 1 coordinate bond here. 1 coordinate, but here we don't show through the arrow the word Werner. According to Werner's theory, it has to be shown with the continuous thick line. So this is the way how to show according to Werner's concept. Thick continuous line. This is ammonia. This is ammonia. And this is another ammonia molecule through the coordinate bond, but we show with a thick line. This is ammonia. This is another ammonia molecule attached to the thick line, that is secondary valency, and 1 is here. At equal distances it has to be there so that repulsive forces will be minimum and the molecule will be stable. You have studied in VC valence bond theory, repulsion theory in class 11. So 1 ammonia molecule is here and 1 molecule is here. So we have 1, 2, 3, 4, 5, 6. In this only we have primary and secondary valency. So here now this compound which we wrote as COCl3 with 6 NH3. So these are with secondary valency and this is with primary valency alone. Then a compound of ammonia with chloride and ammonia is also found to exist, where only 5 molecules of ammonia were attached. And when this was put up in water, 1 mole, then it established COCl2. Now look here. Coordination number, as I told, is 6, but here only 5. So coordination number has to be 6, ligands have to be 6. So there will be 5 ammonia ligand and 1 chloride ligand. So how many chlorides are left over here? Only 1. This is gone to this. So 1 will remain attached to this cobalt as ligand with 5 molecules of ammonia in your complex entity, that is your through the coordinate bond, and there will be two chloride ions separated. Two chloride ions separated means here there will be two positive charge. In the previous case you saw there were three positive charge. In this case, this what will be that is your what you say it the coordination number 5 and 1 6, and oxidation state of this you can calculate what it will be. Cobalt is X, chloride is -1, ammonia is 0. This is equal to +2 means just 2, and this will be gone there -1, it will become +1, so it will be 3. So oxidation number will remain 3, coordination number is remaining 6. But what do you see that we have one chloride ion that is there what as ligand, and this chloride ion, so this chloride ion, this is attached to cobalt central metal atom through the secondary valency as well as with the help of primary valency. So as I told, any anion which is attached to the central metal atom through secondary and primary valencies both, then that negative ion cannot dissociate. That's why we have only two chloride ions out. So if we will draw the structure for this, what structure we will have? Cobalt, and we have got three chloride ions, and this chloride ion is attached, one of this is attached with the primary as well as secondary. So dotted line as well as continuous line, thick continuous line. Then we have got 5 ammonia. So one of the ligand we have shown here, that is the 5 more we have to show. So one ammonia here, so we have got how many ligand? 1 and 2. So 4 more. So 1 here, 1 here, 1 here, and 1 here. You can make it thick. This is ammonia. You can make it thick. This is ammonia. You can make it thick. This is ammonia. And this one also thick line, that is ammonia. So this is here. So you can see here that two of them are dissociable, are shown with only primary valency dotted line. One chloride ion, this is attached to the central metal atom through the secondary valency as well as primary valency. So this chloride ion is not getting dissociated. Now one more example you see of the same compound, cobalt chloride linked with ammonia, COCl3 and 4NH3. In this case, it is found if it is 1 mole taken and it is when put up in water, what do we get? Look here. Coordination number of this will remain 6, but we have 4 ligands of ammonia, and so 2 more will be required from here. So we will have Cl2.4NH3. So 4 and 2 6, we have got coordination number 6. Here coordination number 6. So secondary valency is based on it. 6 secondary valency. How much is left over? That is one chloride ion is dissociable. So there will be one positive charge and this is dissociated ions. So from 1 mole, 1 chloride ion is getting dissociated. 2 of them are attached through primary valency as well as through the secondary valency. So if we calculate oxidation state here, this is X minus 1 into 2 plus 0 is equal to 1. So X is equal to X minus 2 is equal to 1. So X will be is equal to 3. So oxidation state is still 3. So this is primary valency. So three of all these three are attached to the primary valency. Out of these three, two of them are attached with the secondary valency also. So we'll draw the structure. What is the structure? Cobalt. One. Same like previous one. Chloride, chloride, chloride attached to the primary valency, and two of them are attached with the secondary valency. They will remain apart so much that the repulsive forces are minimum. So that's why we will not take crossover opposites to keep them far. So we have got 2 ligands, and so 4 more ligands at equal distances. So this is with the thick line, this is with the thick line, this is also with the thick line. This one also you have to show with the thick line. So ammonia is attached here, ammonia is attached here, ammonia molecule is attached here, ammonia molecule. So thick lines are your secondary valency. This is purely primary one, and 2 chloride ions are attached to primary as well as secondary valency. So this was about Werner's theory and its postulate and its structure. And so the modern theory, this Werner's theory could not explain many other properties which were there. Many properties were explained through Werner's theory, but still some more properties were there which is shown by characteristics shown by complex compound, but could not be proved through the Werner's theory. So the modern concept, modern theory is given that you have to study in detail, and so the structure which they have adopted, the modern structure, how they started writing complex compound, as we have seen in the first day class, that is that a compound, the complex entirety is written here. If you remember, we had K4FeCN6 molecules. So here central metal atom, and this is your ligand. Ligand is written in the small bracket if they are more in number than one, and ligands are diatomic or polyatomic, and this is called complex entirety, you know very well. And the ionosphere is written outside if it is positive before complex entirety, if it is negative after complex entirety, that we have seen in the previous class. So we have done this example, CO, Cl3 and 6NH3. So according to that modern theory, how the structure should be written: cobalt with NH3, ligand in the small bracket, it is polyatomic, so in the small bracket, and 6 is the coordination number outside at the base of the small parenthesis. And this is your complex entirety, and this chloride ion will be written outside. This is ionic sphere. So this is modern concept, and this is Werner concept. Now another example which we have done: CO, Cl and 5NH3. This is according to Werner. So modern theory, cobalt and Cl, no dot, this will be not even the small bracket because it is monoatomic, so we'll write quite close, and NH3 polyatomic, coordination number at the base, bracket close, and we have 2 chloride ion here. According to Werner's theory, we have to write, so here this was written like this, if you remember, +2, and here 2 chloride ion, this is, so here Cl2. So this is warning. Then another example which we have done, COCl3 with 4NH3. And this you will be writing CO, and here 2 will be attached, so Cl2 and NH3 whole 4 and only 1 chloride out. So this is modern concept, this is Werner concept. So you have seen here. Now another thing about this modern concept, you remember, when we write ligand here, central metal atom or ion, and then we write ligands, and then here. So these ligands should be in this order. First anion, all negative ligands, then neutral, and then cationic, positive ligand. And if we have more than one anion, then they should be written alphabetically. IUPAC system of nomenclature, you know that we have to write alphabetically. The first letter of their name, not the prefixes, mono, di, tri, dis, bris. No, only the name. If the name is chloro, then C. Dichloro, then D will not be considered. Chloro, C will be considered, will be written according to the alphabetical order. So, in the next class we will do IUPAC system of nomenclature of these compounds. But now I will teach you one more thing which you need to know. That is, there is a compound that is also called a complex compound. That is double salt. So, double salt is also a complex compound, like coordination compound, but it is not a co-ordination compound. So what do you understand here? That coordination compound is a complex compound. Okay, coordination compound is a type of complex compound. Double salt is also a type of complex compound. But double salt is not a coordination compound. So you have to study now the difference between the double salt and the complex compound. So you will see the difference between double salt and the complex. Rather I should write coordination, then it will be more appropriate. Co-ordination or coordinate, right? Should I coordinate compound? Okay. So, example, double salt. You have studied potash alum. K2SO4 point Al2SO4 whole thrice 0.24 H2O. You have studied this compound. This is potash alum. And last year you have studied a compound, ferrous ammonium sulfate, FeSO4 point NH4 whole twice SO4 0.6 H2O. This is also called Mohr's salt. Ferrous ammonium sulfate. And coordinate compound, many example you know, K4FeCN61, and today you have seen CO, Cl 0.5 NH3, and Cl2. This type also you have seen, and one we have done earlier, neutral one. This one also we have done. Here complex entirety is negative, here complex entirety is positive, here complex entirety is neutral. So these examples we have. So what difference you saw? Here no square bracket is used, and here is the square bracket used when we write the formula. So double salt, the first point what you should know, these salts do not retain their identity, or do not retain identity of their constituent particles. What are the constituent particles in a potassium? K2SO4 point, Al2SO4 thrice 0.24H2. What it is there? Now just see. When this will be dissolved in water, we will get 2 potassium ions, and then we'll get 3 and 1, 4 sulfate ions, and we will get 2 aluminium ion, and there will be water molecules. So this salt, when this is dissolved in water, it will give test for potassium ion, it will give test for aluminium ion, it will also show test for sulfate ion, and also it can show test for water, but that will won't perform because we are already dissolving in water. So ions are not retaining their property. This compound is not retaining its property as a whole. All these ions, they are getting dissociated. Whereas in this compound K4 FeCN6, when this you will dissolve in water, what you have seen that it gives 4 potassium ion, and this will remain as it is. The complex entirety that will remain as it is. So this will be giving test for potassium ion, no doubt, because this is ionic sphere, but it will not give test for Fe, it will not give test for cyanide. Instead, it will give test for ferrocyanide as a whole. So complex part is this, and so complex in this, ions are not getting separated, so it is retaining its property. So what is here? The second point you can remember, they exist only in solid state. In solid state they will have their double salt property, but they have both in solid and in solution. They will retain their identity. They will not lose their identity. Double salt. So these double salt points, this is a combination of 2 salt, K2SO4 point NHAl2 SO4 whole thrice 0.24 H2O. This is one normal salt, and it has its own crystalline nature. This is second normal salt, and it has its own crystalline nature. And when these two are mixed, what ratio here? 1:1. Then they are forming a double salt, And this double salt, which will be found with 24 molecules of water of crystallization. So this whole thing which will be coming out together, all that will be also having crystalline nature. So this is crystal 1, this is crystal 2. This may have a different shape of crystal, this may have another shape of crystal, and when this compound is formed, potash alum, this will have also crystalline structure, but that crystalline structure will be different from these two crystalline structures. It will have its own set of property. A double salt in the solid state will have its own set of property. If this is the salt not put up in water, potash alum, then it will not have property, this salt as a whole will not have property individually of this salt or of this salt. It will have its new set of property. And whereas here, if you put this in water, then you will see that the same solution which is formed from this, that is showing property of this salt and showing property of this salt individually. So this is very important thing, and so this question is asked many times. So how you can distinguish this, whether this is a salt? If you are given a salt X, name is not given, it is performing test for sulfate ion, test for potassium ion, test for aluminium ion, then it is a complex salt or a double salt. You can very easily say it is a double salt because in this two metals are there and both metals are showing their test. So none of the metal is your central metal atom, because central metal atom will not be separated. If it is asked K4 FeCN6, if this is put up in water, and so you will not get test for iron, but you will get test for K4 potassium. You will not get test for cyanide. Okay. Now see another example. If you take FeSO4 point NH4 whole twice SO4 0.6H2. So this will give you test for iron, but here this is a coordinate compound, will not show test for iron. This will give you test for ammonia. This will give test for sulfate. But here you will get only test for potassium and for this as a whole. In this case you will get test for this ion, test for this ion, test for this ion already there. So I hope this will be clear. So double salt is formed when the metal, central metal atom which we have, the metal atom, this metal atom is linked through the anions, negative ions, with what? They are only attached to this, and they are attached to the normal valency. Normal valency. So in double salt you have only normal valency, whereas in coordinate compounds we have beyond normal valency. You have seen that is secondary valencies, or maybe a combination of secondary and primary valency. So this was about double salts today, and I hope it will be clear. So double salt is ionizable. In water it will dissociate into all its ion, whereas complex salt, when you put, that is coordinate compound, when you put in water, it will form only ionic. The ionic sphere will form ion, and the coordinate complex as a whole will be forming its ion. So that's all. So in the next class we will do IUPAC system of nomenclature of complex compound. So till then, bye.